Welcome back to the next lecture. This is the satellite communication, and we had discussed orbital perturbations. What we have observed in the previous class while discussing these orbital perturbations, using the Kepler's law, whatever orbital parameters we have derived, suppose velocity, time, period, and what all the things orbital parameters we have derived, and for that we have assumed the Earth is a pure, completely spherical object, and there are no other additional effect which is acting on the Earth's surface or the actual satellite also. But in practice, it is not true. There are many factors which can create error, which can create deviation in your orbital parameters. So we also have highlighted some of the parameters. One of that is non-uniform Earth gravitational field, effect of Sun and Moon gravitational field, solar radiation pressure, and atmospheric drag for low Earth orbit. In this lecture, we are going to discuss all the effects, all the effects on the orbital parameters. So first of all, let us see the effect of Earth asymmetry. That means the effect of non-uniform gravitational field. If you see the Earth, it's not a completely sphere. That means the equatorial radius is not constant. In an average, if you see the polar diameter or the polar radius is less in comparison to equatorial diameter or equatorial radius. So if you make a Google search, then you can find the average radius of the Earth in the equator is about 6,378 kilometers. Whereas towards pole, if you measure, it is coming around 6,356.75 kilometers. So every time we consider 6,378 kilometers. So this is the by default the Earth radius we have considered on all the previous calculation what we have done. But if you see the reality is not same. In reality there are difference, and any difference if you do the same calculation using this value, this radius value, then you definitely will obtain some different result. And hence, due to that, there are slight deviation in the orbital parameters, what we are really getting. So what we are calculating and what we are experimenting or what we are really getting, they are slightly deviated. And not only that, we also have non-uniform acceleration due to gravity. If you see towards equator, it is 9.78, which is meter per second square. If you go to the pole, you will have higher gravitational force, that is 9.83. That is called the acceleration due to gravity. Towards pole, we are experiencing high gravitational field, whereas towards equator, we are experiencing less gravitational field. So this is because of the shape. Since the shape of the Earth is such that the equator is quite bulged. If you see the equator portion, it is bulged. This is bulged portion. And that is the reason why towards equator we are experiencing less gravitational field and we are experiencing high gravitational field towards the polar regions, whether south or north. So due to this force on the satellite varies with its position, because satellite is moving around the earth, and since the gravitational forces are different, so all satellites are experiencing different amount of force. And this additional force tends to drift the satellite towards equator poles, and satellite tends to accelerate or decelerate from its allotted longitudinal location. So try to analyze the thing, what is happening. You are experiencing high gravitational field towards northern pole and southern pole. Getting the point? That means when the satellite goes towards north or south, it is experiencing high gravitational field. And this gravitational field is towards what? Always gravitational field acts towards which direction? Always all in Earth, we experiencing the gravitational field towards the center of the Earth. Every time the direction of gravitational force is to the center of the Earth. So when the satellite moves to the higher altitudes, that means to northern or southern hemispheres, it will experiencing high gravitational field. That high gravitational field, there is acceleration, there will be acceleration and deceleration. That if a satellite, let me show it in this picture, but you have to analyze, this is Earth, okay, and the orbit of the satellite is this one. This is the satellite and this is the Earth. And let me show this line, okay. This line represents the equator. Now, if you see this particular satellite, it goes towards north. It is going above equator. And as it moves above equator, it is experiencing high gravitational field. So when the satellite is moving more and more towards north, it is experiencing high gravitational field and there is a deceleration. The velocity of the satellite will decrease because of the increase in gravitational force. And when the satellite comes in this direction, that means in this direction, so the movement of the satellite is in the same direction and in which your gravitational force is acting. So what you are experiencing here, high acceleration. So whether it is deceleration or acceleration, all the forces are acting towards the equator, towards the center. And this particular force tries, or with this gravitational force, tries to drift the satellites towards the equator. So when the satellite is rising above, when the satellite is rising towards north, okay, the force is acting in opposite direction. And due to this force, it tries the satellite to place it near the equator, although it is not happening, but still the force is acting, the gravitational force is acting on the satellite. So here also, when the satellite is moving, the gravitational force tries to put the satellite in the equator. Now, if you see, when the satellite now comes in this way, here gravitational force is in this direction. In this direction, your gravitational force is acting. So here, it tries to put the satellite in this equator. Now, when the satellite moves in this direction, again it will be accelerated. So at this point here, the satellite will be accelerated. Accelerated up to what? Up to equator. Up to equator, the satellite will be accelerated. And when the satellite rises above the equator, again the gravitational force will acting and it will reduce the velocity of the satellites. It seems that the gravitational force tries to put the satellite on the equator, but although it is not happening, right? So there is acceleration and deceleration. When acceleration, when it happens, when the satellite is moving in the same direction of the gravitational force. Deceleration happens when the satellite is moving in the opposite direction of the gravitational force. Okay, so due to this acceleration and deceleration, there will be change of longitudinal location. So the whatever the longitudinal location of the satellite, it will be deviated. Okay, so changes happens here. Now you see, this is practically has been observed these 2 points. Okay, if this central region, the central solid region is the Earth, and this particular circle represents the orbit of the satellite, and this these coordinates which I have represented by 75° east, 162° east, 252° east, and 348° east. So what these coordinates? These coordinates are nothing but these are the longitudes, because longitudes are in east on as well as west. But I have not represented here anything west, because the whole 360°, earlier concept was what I expressed to you earlier. At a 0° longitude in eastward direction, we move 180°. In westward direction, we move 180°, such that the whole angle will become 180 plus 180, that is 360°. That was the thing. But now what in this particular diagram, what I have represented, I have represented a single direction, that is the eastward movement. So if this is the 0° longitude, I am moving towards east and I am reaching at this point. So I am completing 360° rotation in eastward direction. Okay. So suppose this particular point represents 0° longitude. So this particular point will represent 180°. So consider this, you may consider this as east longitudes. You may consider this as west longitude. So this is one kind of nomenclature you can follow. Otherwise, what it has been done here, it has completed the whole angle 360°. So this is 360°. So since it is moving towards east, so that's why all the longitudes are represented by east. So this angle starts from 0° to 360°. So 0 means it is 360°. Okay, so this is the longitude. So this orbit represents the what is the longitude with respect to your Earth. All right. Now, what has been observed? It has been observed in reality and in practicality. There are two different longitudes. One is called 75° east, another is 252° east. So these two longitudes are the stable locations. That means the satellites tries to remain fixed at this particular location. If the satellite is at 162° east or 348° east, so these are the unstable points. Okay, so due to the gravitational force, those satellites will come back to this position, either 75° east or it will come back to 252° east. Okay, but as far as the uh, uh, Indian satellites are concerned, particularly those um, insats. Okay, so those satellites are in a latitude of 74 74° east longitude. So we are fortunate enough. Our country is located towards east direction of 0° longitude. We are very much fortunate. So that what happens, our satellites, when they are at 74° east longitude, so they remain stationary with respect to any any station, any ground station on the surface of India or on the surface of our country. Okay. So this is what I have shown, that there are some longitudes which are considered as the stable location, and it is because of the gravitational force which is acting. So at the stable point, any perturbation will make the satellite back to the stable, drift back to the stable point. So due to non-sphericity, the stable and unstable points are not 90° apart. Again, one more point. So if you observe, this is one stable point, this is one stable point. So these two stable points are not 180° apart. Similarly, this is stable point, the adjacent unstable points are 162 and 348. They are also not 90° apart. It is because of the Earth is not a sphere. So that is the reason the stable and unstable points which are adjacent to each other, they are not 90° apart. So any perturbation at unstable will drift the satellite to the nearest stable point. So due to that, the satellite will be pushed or it will be drifted to the nearest stable point. And due to moment of inertia, the satellite crosses the stable point and starts oscillating around the stable point. Are you getting the point? When the satellite in the unstable point drifted to the stable point, it has some moment of inertia. And due to the moment of inertia, the satellite cannot remain at this stable point. Because of the moment of inertia, the satellite will move from this unstable point to stable point, and still it will come here. And still it is again unstable point, and again satellite will come here. So the satellite will oscillate like this around the stable point. It cannot be remain stable. It will oscillate to and fro from the stable point. And that happens because of the moment of inertia. It has some momentum. And because of that momentum, it happens like this. And this direction, so this movement, this is called the east-west movement of the satellite. Okay, so this is the east-west movement of the satellite that needs correction. So we need some correction at this particular errors. Okay, and remember the east-west movement of the satellite happens because of non-sphericity of the Earth, since the Earth is not a sphere, and the gravitational force is non-uniform. So that causes the east-west movement. Okay, now come to the next topic. So we have another effect, that is the effect of sun and effect of moon. Okay, so any question? Nothing. So you see, observe here. This is the sun, which is the central object, and around the sun, the Earth is moving. Moon is a natural satellite. Moon is also rotating around the Earth. Like the man-made satellites or artificial satellite, what we are launching. So moon is also rotating around the Earth, as well as all the artificial satellites which we are launching, they are also rotating around the Earth. So what the point to note here is that as our Earth is rotating around itself, Sun is also the central object that is also rotating around its own axis. So if you consider here this particular straight line, represents the orbital plane of the Earth. That means what happens? The Earth is rotating on this orbit. Okay, so if I draw, it is very difficult to represent here, but if I will show, suppose this is the orbit. My drawings are not perfect, but I assume this is the orbit, and this side I cannot draw. Okay, here also I am drawing. So this is the orbit in which the Earth is moving around the sun, and this straight line represents the orbital plane. Okay, so let me erase this. All right, so this straight line, this represents the orbital plane. That means it is the plane in which the satellite is rotating around the sun. But look at the sun here. The axis of the sun is not 90° with respect to the orbital plane of the Earth. That means the sun itself is tilted. Sun is little bit tilted. Get the point? So how much angle sun is tilted? 7.3 degrees the sun is tilted. Okay, so that means this angle is not 90°. Rather, this angle is 90°. This angle is 90°. But this angle, that means from the plane of Earth's orbit to the axis of the sun, this angle is not 90°. So this angle is how much? 90° minus 7.3. So that will it will come as 82.7°. So this angle is 82.7°. The same way, if you observe, our Earth is also tilted. That you know from your childhood. Earth is bent at an angle of approximately 23°. Earth is bent. So this particular straight line represents the orbital plane. That means the geostationary satellites, they are moving in this orbital plane. So your Earth is tilted at an angle of 23°. Okay, and look at the moon here. This particular straight line represents the orbital plane of the moon. Got my point? So with this understanding, when all objects are moving, keeping the sun as the center, sometimes what happens, because Earth is moving, satellite is moving around Earth, moon is moving around Earth, Earth is moving around sun. So now at this particular image, you see the satellite is now in between sun as well as moon. Okay, now when Earth comes here, when our Earth comes here, since I have no space in the right side, I'm drawing a small thing. When the Earth comes here, so your moon might be somewhere here, satellite might be somewhere here. This is the moon, this is the satellite. Okay, because the Earth is rotating around sun. Sometimes Earth will come here, sometimes Earth will come here. All right. Then what happens if you observe that when the satellite is here at this particular location, it is observing only the force because from the moon. Now, when the satellite is here, it is observing force from the moon as well as from the sun. That means at these locations, the satellite lies in between moon and sun, but where it is not. Because the satellite is outside, away from the Earth. It is just the satellite is opposite side of the Earth. So this side sun is there, this side satellite is there. So it is just opposite side of the Earth. So it will experience less force from the sun. But it definitely will experience some force from the moon. But here at this location, it will experience, because here the satellite is lying in between Earth and sun. So it will experience it will experience force from the moon as well as from the sun. So in every rotation, what the force which is acting on the satellite from the galaxy, the forces are acting from the moon, forces are acting from the sun, that is not uniform. Sometimes the satellite experience forces from the moon itself, not from sun. Sometimes it will experience forces both from moon as well as sun. So in general, the total force or the average force is not uniform. Okay. So yeah, ecliptic, that is the Earth orbit plane around the sun is 70. Yeah, this is what I told you. It is 7.3 degree. Okay. And this is our Earth is 23-degree bent. Moon's orbit plane around Earth is 5-degree inclined to Earth equatorial plane. So if this is the Earth equator, if this is the Earth equator, your GEO satellite, assume this satellite is a GEO satellite. So GEO satellite is exactly the orbital plane of the GEO satellite is same as the equatorial plane, but moon's orbital plane is 5-degree above the equatorial plane. But satellite's orbital plane is same as equatorial plane, but moon's orbital plane is 5-degree above equatorial plane. That is why. So net gravitational force due to sun and moon is not in satellite's orbital plane, and we'll try to change the inclination of the satellite. So that will make the inclination, make the change of inclination of the satellite. That means if you see one force is acting from the top of the satellite, another force is acting from the bottom of the satellite. Here, the force is only acting from the top of the satellite. There is no force from the bottom of the satellite. Okay, so what in general is that the forces on the satellites are acting in both the directions, sometimes in one direction. So what will happen in that case? The position of the satellite will change here. Understood? Now, if here if two forces are acting, here only one force is acting. So definitely if one force is acting means it will be drifted towards north, because there is no force which is acting towards south. But here two forces are acting. So which forces is higher, the satellite will be drifted in that direction. Right? So the net force will try to change the inclination at the rate of 0.85 degree per year. So since the Earth is moving, so Earth completes 1 year to make 360-degree rotation around the sun. So that we consider as 1 year. So in an year, so generally there is an approximate change of 0.85 degree, the position of the satellite. So it will change either 0.85 degree north, 0.85 degree south. Like this, the position of the satellite either towards upward or towards downward, it will change. Okay, so this movement is called north-south movement, because sometimes the satellite is pushed towards north and sometimes it is pulled towards south. So there is this change in degree 0.85 inclination angle. So this change is in a direction of north or south. So this is called north-south movement. So earlier we have come across east-west movement of the satellite, and that happens because of non-uniform spherical sphericity of the Earth and non-uniform gravitational force. And this movement is called north-south movement. It happens because of the sun and moon gravitational force. So the north-south movement of the satellite happens because of sun and moon gravitational force. Sometimes operators intentionally keep the initial inclination higher and let his natural force reduce the inclination to 0. Okay, so in order to correct this error, because whatever angle, whatever location we will send the satellite, the location will change because of this. So what the people are doing, they will by default they will introduce this angle so that because of the gravitational field, this much amount of degree will be considered as 0. Okay, but it is a slow process and ground system has to use tracking. So actually, whatever this movement happens, north-south movement, it happens throughout the year. So this is a very slow process, and we can track the satellite by using telemetry and tracking system. We can track the and ground station. So yeah, exactly. What is that? I was telling it is called the north-south movement of the satellite. So change of inclination needs 10 times more thrust than change in longitude drift of ellipticity. Now come to one more parameter that is called atmosphere drag. So we have discussed two parameters now. This is the third parameter. This is called atmosphere drag. What do you mean by atmosphere drag? So atmospheric drag is related to the gravity. For example, and this is more dangerous. This effect is more dangerous on the lower Earth orbit satellite because these satellites are located very close to the surface of the Earth. But particularly, they are located around 150 kilometer to 1500 kilometer. So 150 kilometer is a very close. Even we experience high gravitational field at such a distance. But if you talk about the geostationary satellites, which are around 36,000 kilometer, they will experience less gravitational field. So this effect, atmospheric effect, will be less upon the geostationary satellite in comparison to LEO satellites. And because of that, the velocity of the satellite will reduce, and not only velocity, it will the satellite will be heated because of that, because it will create friction. Okay, so due to this friction, body temperature of the satellite will increase because when the satellite is very close to the Earth's surface, so very close to the Earth's surface, the atmosphere of the Earth is very dense. If you go above and above, the atmosphere becomes lighter. Okay, and as you come towards the surface of the Earth, the atmosphere becomes more denser. More denser means more friction you will observe. So more friction means when an object is moving, so it will experience the friction from the atmosphere. Okay, so when the friction happens, the temperature will increase. Okay, that you can see that when an aeroplane is moving, and suppose it is heavily raining, and aeroplane is traveling, but you cannot observe any water droplet uh, on that on the side of the aeroplane, because at a such speed body of the aeroplane will be heated. Okay, so no water droplet you can observe. even if it is raining. So that is what, due to this friction, body temperature of the satellite increases, and there is chances that the satellite may burn if it will be too much heated. Yeah, and sometimes, in LEO satellites, they are launched 180 kilometer, which I have noted here, no, 150 kilometer. So some cases we are launching the LEO satellites as low as 180 kilometer. Okay, so which is very close to the Earth's surface. And approximately they are around 1000 or 1500 kilometer. Some LEO satellites are there. Okay, but as low as this is the lowest height of the LEO satellites. Okay, so this is one of the atmospheric effect. Another effect is called the solar radiation pressure. So what happens here? It is proportional to the surface area projected towards the sun. So how much surface area of the satellite is facing towards the sun? That much surface area will be subject to the solar radiation, will be subjected to solar radiation. And because of solar radiation means what happens, it is subjected, that much portion of the satellite will be subjected to the solar gravitational field. So more is the surface facing to the solar radiation, more will be the gravitation. So that will lead to north-south movement. Okay, so this is all the things we have discussed in the orbital launch of the satellites, in how different stages we are launching the satellites. And if there is a change in orbit of the satellite, then how much amount of velocity change happens? What is the thrust additional velocity we require when we change the satellite from one orbit to the other orbit? And by launching the satellite towards eastward direction, how much amount of fuel we are saving? And over to that, we have discussed the reality. That means what are the effects which have not been considered in the Kepler's law? Means how those effects affect the orbital parameter of the satellites. So with this, we will complete this particular chapter of satellite communication. And next class tomorrow, we will start a new topic on satellite communication. And if you have any question related to this, then let us discuss.